Welcome to Savitha Dental College Lecture Cast in Biostatistics. This is Dr. Deepak, and we shall see the continuation of descriptive statistics from our previous session. So, the primary areas we are going to cover under this session include the histogram, the box plot, the normal distribution, central limit theorem, and a little bit about kurtosis. First, let's look about the histogram. A histogram is a graphical way of representing data which is easy to understand which group has the highest number and by how much are they leading compared to the other groups. For example, if you look at this data, we know that blue is the highest number, but it's not easy to know by how much the blue is higher than purple or red. But a simple reorganization into a histogram will give you a much clarity into how exactly each group varies and by how much. So moving on to the next part of today's class is the box plot. This is a special type of graph primarily used to represent non-normal distribution. For example, if you take this data which is spread from 3 to 35, you notice that there's a lot of data distributed closer to 3 and there are few data points distributed closer to 35. And when you calculate a median for such a group, it's around 12. Median is the 50th percentile, and that's how it's represented in this chart. We also notice that the 25th and the 75th percentile also vary considerably. For example, since most of the values are located on the lower end of the median, you notice that the 25th percentile is closely located to the minimal value, whereas the distance between the 50 and the 75th percentile is much higher, and that of the 75th percentile and the maximum value is also higher, as seen in this graph. So a box plot would normally represent this as a bar with a thick line representing the median and the two terminal ends representing the two quartiles. The lower quartile is called the 25th quartile and the 75th percentile is called as the third quartile. So the interquartile distance also signifies the distribution of data. If the interquartile distance is higher between one quartile and the median, it means that the data distribution is uneven and that could affect the results of your statistics. When you have multiple groups like this, you could compare the interquartile distance of multiple groups to know about the characteristics of each group. A completed box plot would look like this, wherein you can see the minimum and the maximum values plotted along with the bar. So remember again, whenever you look at the box plot, the thick line in the middle is usually the median and it's not the mean. And the ends of the box represent the first and the third quartile. And the minimum and the maximum values are represented in the outer T-shaped bars. The next topic is normal distribution. We have already covered normal distribution in our previous session, but however, we have covered it with little more graphic and vivid detail in this video as well. So a normal distribution is nothing but data distributed equally above and below the mean. So if you have the mean and you have a data set where the number of values above the mean and the number of values below the mean are similar, we call it normal distribution. Almost all things in nature follow normal distribution. Whether it's the length of your hair or a size of a planet, everything would follow normal distribution. For example, you could have people with very long hair, but there will only be few of them, and you could have people with no hair at all, and there will be very few of them. Majority of the people would have an average length of hair, and they would be lying around the mean hair length. The same thing would apply for planets. You could have extremely large planets, but there'll be very few of them, and you'll have very small planets, which could also be very few of them, but the majority of the planets will lie around the mean planet size. However, normal distribution is when you have more data located above the mean and less data located below the mean, as you can see in this example. It could go the other way around also, but we have an example for that. So as you can see, the area shaded shows that the amount of data above the mean is much higher than that below the mean, and such a distribution cannot assume that all the participants in the study are similar or evenly distributed. This is another example for non-normal distribution where it's skewed towards the left. And you can see that there are more values located below the mean than the values above the mean. But you should remember that whether the skew is towards the right or the left, as you increase the number of study participants or the sample size increases, all data would eventually return to normal. This is central tendency. And moving on to the next topic, we can talk about the central limit theorem. The central limit theorem is one of the most interesting prospects of normal distribution. According to this theorem, 68% of all values will lie within one standard deviations of the mean. Here you can see in the dotted lines the sigma 1 plus and the sigma 1 minus is the standard deviation of the mean. And 68% of all values will lie in any normal distribution. And the second theorem states that 95% of all values will lie within two standard deviations of the mean. And the third rule of the theorem states that there will be 99.6% of all values lying within three standard deviations of the mean. This is interesting because once you know this kind of ratio exists, you can predict the number of percentage of population or the number of people above a cutoff value based on the mean and standard deviation of that group. For example, let's assume the mean IQ score is 100 and the standard deviation is 15. If you want to know the percentage of people or the percentage of data with more than 130 IQ points, you can deduct the answer as follows. The data between 85 and 115 scores would be 68%. The data between 70 and 130 would be around 95% because it's two standard deviations from the mean. And the data below 70 and above 130 would be 5%, which is basically outside of 95%. And the data above 130 would be 5 divided by 2, which is 2.5%. So based on this deduction, we can say the number of people in this world with more than IQ of 130 would be 2.5%. So this is a tremendous value for statistics, and that is why we try to work with normal distribution. Because when you have a non-normal distribution, such a simple deduction is not possible. So the next major topic for today's session is the kurtosis. Kurtosis nothing but shows the steepness of the bell curve. In other words, if more and more data gets accumulated around the mean, you notice that the standard deviations move closer towards the mean and also that the bell curve becomes much taller. And this is the property of kurtosis, and it also shows that data when you get such a sharp curve like this, such a steep kurtosis or a curve with such a steep kurtosis will have data which is more homogeneous. And when the kurtosis is very shallow, you would expect the data to be more heterogeneous, meaning there'll be a lot of variation within the data or within the participants within the group, and so you would expect those factors affecting your results. So with that, we have finished biostatistics, descriptive statistics part 2, and thank you and hope you have a nice day.